Okay, so good morning. My name is Matteo Interlandi, and this is the summary of my research activity that I carry on during my PhD studies. My tutor is Professor Sonia Bergamaschi, and my co-tutor is Professor Letizia Tanca, and I forgot to put it on the slides. So during my PhD, I basically work on 3 different topics. The first one is keyword search over databases, and the other 2 are more related to distributed system and declarative programming of distributed systems. So starting from the first one, basically the problem to retrieve information from relational data sources is basically that we need 2 knowledge. First, the knowledge of a query language, such as SQL, and then also the knowledge of the schema that we are going to query. Of course, these are not technical people are not able to query relational databases because usually they miss this kind of techniques or the information about the schema. So this new branch of information retrieval, the keyword search, start to apply also for databases. And basically, we can do a review of the literature of keyword search over databases. And we found that basically there are 2 different approaches, let's say. One is at the instance level, and one is at the schema level. Basically, the difference between the 2 is that one, the keyword search is applied directly over the instance of the databases. So if you have a large data set, that's gonna have some efficiency problem. On the other side, the schema level, they just care about the schema, the information containing into the schema of the database. So we have that we don't care about the information about the instance. So the results that are returned from the search can be wrong because they're just at the schema level. So our idea is trying to merge these 2 different levels in 2 different perspectives. So we have a user perspective and a database perspective. From the user perspective, basically, the idea is to try to unlock the information that the user is putting into the keywords when you do a search, and try to unlock these semantics that he encode inside the keywords. And we implemented this kind of a perspective in a in a software that is like a forward module. And this forward module basically implements 2 hidden Markov models. And this hidden Markov model basically try to map the keywords with the terms that are inside the database schema. We call this mapping as configurations. For the database perspective, instead, we want to summarize somehow the information that are encoded inside both the schema at the instance level. We call this module as backward module. So to do that, we basically capture metrics from the instance using a mutual information-based algorithm. And then we create a weighted graph starting from the schema and these metrics. And then we apply a standard tree algorithm on top of this graph. And the result from this algorithm, we call the result from this algorithm as an interpretation of the previous configurations. Now, then we merge the database and the user perspective, and we ranked all the possible results. So the final result occurred as explanation of the configuration and of the interpretation, and this is implemented in a combiner module. And basically, the result is that we are able to find the mappings between the keywords and the data structure of the databases that are most likely to have the semantics of the user and the most likely to actually belongs to the database, to the instance of the database. And to implement this, we use the Dempsey-Schefter theory of probabilities. So this is the software module, and it explains also how which is the process of the keyword search. So we started from a keyword that is as input to the system, and then we apply, as I said, the 2 hidden Markov model. Basically, we choose 2 hidden Markov model because we want in one we encode some heuristics that are basically taken from the database, and the other one instead we want to use the feedbacks of the user when the results are returned to the users. So this basically, the idea about these two different approaches is that one basically give a basic status of the forward module, and then when the software is continually used by the users, we basically can we train these systems so that we have more refined result at the end. Then the result computed by the two hidden Markov model are combined by the combiner module, and as input to the combiner module, we give two parameters that encode the uncertainty that the user have in the two different hidden Markov model. So we have that, for instance, in the a priori case, when the software is just started, we have no information about the feedbacks of the user. So we basically have we are more sure that about the result of the a priori than with the feedbacks. But then when the user continually submit queries to the system, we have that the feedbacks, of course, will overcome the result of the a priori. So we can put more probability over the feedbacks based hidden Markov model. Then from all the top K configuration, we create the graph, the weighted graph using the matrix over the edge, and each node in the graph is a term of the schema. We apply the standard tree, and then the final results from the combiner and the interpretation are combined. The database a database query, a SQL query is created. We query the database and we return the result to the user. We do this is some chart from the experimental evaluation of the system. We have that from the efficiency point of view. We have that this is the forward, this is the backward. These are different settings for the different result that we can return. This means that top 1 means they return just one result, top 10 that we return 100. And so we have that for the forward module, we have the worst case is 1 second, the best case is 1 second, the worst case is like 5 seconds. And these are different query settings. For the backward case, instead, we have that in the best case it's like few milliseconds, and in the worst case around 50 seconds. For the effectiveness, we use two different data sets, DBLP and Mondial. For the DBLP case, we have the difference between the two data sets is that one have a big instance, while the other one is a very complex schema. For the big instance, even for the top one, that means that we return just one result, and if we have almost 95% that the correct result, the return result is the correct one. These are different settings for the training. So we have that just for two cases where we use basically unsupervised and 1/10 supervised in the data set. For all the other cases, we have that we reach almost 95%. For the Mondial, instead we have from 80% to 90%. And we also do some experiment without considering the database. So we just basically accumulate the feedbacks from the user. We create from scratch a new database. And even in this case, we can reach around 80% of effectiveness. So concluding, we basically show that an hybrid solution that put together the database and the instance levels and the schema levels is possible, and we can reach good effectiveness and efficacy. These are my papers about these topics. Then moving to the next one. Basically, the idea about these topics is that we want to put together two different approaches. Basically, we want to reason about the distributed system, but usually when you reason about distributed system, you reason about the state of knowledge that all the nodes have in a distributed system. And we want actually to implement a language that is able to, that a user can exploit to implement actually high-level specification using this knowledge state. So as a basic query language, we choose Datalog. So our rule in Datalog is very simple, is in this form, where this is the head, and these are the body. basically each of these can be seen as a database table, and a complete rule basically defines a view over a database table, and when we have no variables inside the rules, we have a fact that means an instance over the database. So the intuition behind this topic is that let's say that we want to compute all the possible paths in a network. So we have nodes and edges that are this green, and we can put all this inside a relation, let's say a link relation. So this link relation which have an instance 1 and 3 if there is a link from 1 and 3, 3, 4 if there is a link from 3, 4, and so forth. So we can you can compute all the paths from every node, let's say doing the transitive closure of the link relation. So we have that we have a path every time that we have a link. This is this rule over there, where we use this form at saying that this instance is stored at this node. So if I put 1 here, this means that this relation is stored at this node. If I put 3, this means that this relation is stored at 3. So now, to compute the transitive closure, we can say that, for instance, we have a path from node 1 to node 4. If node 1 know that there is a link from 1 to 3, and node 3 know that there is a path to 3 to 4. This is exactly this rule. This rule, however, is missing something. This is the knowledge. The fact that I specify, when I say that, I specify that node 1 know a link, and node 3 know that there is a path from 3 to 4. So we basically add epistemic model operators to the language. So now the rule is exactly specifying that. This means that node X know that there is a path from X to Z if you know that there is a link from X to Y, and Y know that there is a path from Y to Z. We can say that this model operator are used in 2 different semantics. In fact, when they use in the body, they basically specify a node state of knowledge. While if they use in the head, they specify basically an action. This means that we modify the state of knowledge of node X by adding the path instance. And this is usually called as knowledge-oriented programming. And basically using this type of programming, we can achieve, we can both reason about a distributed protocol and also program actually a distributed protocol using this kind of language. So we know we name this language Nolog, and a rule in Nolog is basically is the same as a Datalog rule, but now each literal is in this form, where delta is basically a sequence of model operators, and we allow 3 different types of model operators. The K, that means that node I know something, that is what I described before. And then we can also reason about state of knowledge of group of nodes. So we can say that a group of nodes, every node in a group of nodes knows something, or that if we join all the knowledge about all the nodes in a certain group, we have a distributed knowledge of something. We tested this language with, we actually implemented a two-phase commit protocol with this language. Concluding for this topic, we basically have seen that by adding epistemic model operators to Datalog, we are able either both to reason about a distributed system and also to implement high-level specification for distributed systems. And these are the publications related to this topic. Going to the last topic, basically, the idea about this topic is that we know that the programming distributed system is a very complex task, and they often need specialized techniques and experts. However, nowadays we are both living the end of the Moore's law, meaning that the increase in performance cannot be achieved just through increasing R2 speed, and therefore the concurrent and parallel computation must be exploited. In fact, we see this growing architecture based on cloud computing or on multi-core processing. But not even this. We also need actually to exploit distributed computation because we are in the era of big data. So this means that we have this large data set that cannot be computed just with one machine, but we actually need really powerful computation systems. So if we take under analysis the system, the different approach that implements this large-scale data processing, we can basically find that we are two different type of systems. One that is declarative, that is basically the parallel DBMS, and are based on the usual relational model theory. And then instead we have also an imperative approach that is growing in this last year, that is basically all the systems that are, let's say, MapReduce-like. So these systems are highly scalable, fault-tolerant, and they have no theory beyond that. It's just driven by the industrial needs. There is some work that try to merge the two works together, but basically these are just work that try to export a language and interface from one word to the other. This means try to put a declarative language on top of imperative systems. So we have this set of declarative language such as Hive or Pig on top of MapReduce. Or we have some parallel DBMS that try to use some MapReduce-like function on top of them. And then we also have some system that try a systematic merge of the two words. So we have this, let's say, Hadoop DB that try to merge a database system with MapReduce. But instead, we advocate that a more in-depth search must be done and try to reach what is called a declarative imperative approach. This is something similar to what they already tried to do like 40 years ago when they found out that they presented the logic programming, and they found out that when I have an algorithm, I can basically split this problem in two different sets. The logic that is basically static and just say, just specify what problem I need to solve, and the other one is just say, okay, we can have low-level implementation of the solution that will not impact the final solution, but will explain how actually the solution must be computed. This is basically also the basis of the relational databases. So we try to go in this way, and to go in this way, we basically developed an abstract computational model based on what was already researched on the field of relational transducer. So we create a synchronous transducer network, that basically a network of relational transducer. We choose the synchronous case because for the parallel computation, most of the time they actually implement a synchronous system, not an asynchronous system. And this is basically the main difference from the previous approach. They try to the previous approach about declarative networking. So we give an expressive power and complexity analysis of the model, and we investigated three different communication models. One that is really simple broadcasting, one that is hashing, and this is really similar to also what MapReduce do, and then the usual addressing communication model. Then after that, we've developed a declarative language on top of this abstract computational model that we call Datalog. Datalog is basically a version of Datalog that embeds a notion of time and space. Time because distributed systems are evolving entities that change with the pass of time. And space because, of course, it's a distributed system, so we need a notion of locality to the nodes. Rules in Datalog can be of three different types. Deductive rules that are basically the normal Datalog rules. Inductive rules that permit to move, to create the persistent state by moving tuples forward in time. And synchronous rules that instead are used to move tuples from one place to another. This is what we already saw for Nolog. And of course, we have developed a declarative semantics for this language. Then we basically did theoretical work on this language and on this computational model. So we try to define, given the computational model, given this declarative language, to define what it means to be a query to be distributively computable, what it means to query to be parallel computable, and then we found out that we have a taxonomy of queries with different characteristics. So we define the important part of this work is that we define which query is embarrassed in parallel. That means that can be computed without communication. We basically define this epic theorem, and then we prove the Calm theorem. The Calm theorem is a theorem that is a conjecture that was presented 4 or 5 years ago. It was proved for the asynchronous case. And basically this is saying that coordination, meaning coordination and logical monotonicity. This means that for distributed system, coordination is needed just if the execution that I'm doing is not monotonic. This was already proved for in the synchronous case, but we found out that for the definition of coordination that they use in the synchronous case, it was not working. So we define a new type of definition for coordination, and to doing that, we basically take the notion of syncasuality, that is the happen before a relation, and we add some other characteristic to the happen before a relation, and we prove that actually the common theory also work for the synchronous case. I'm almost finished with the time. So after that, 30 seconds.
Yes.
Okay. After that, we basically apply the theory with, we create some algorithm to automatically parallelize declarative query using this theory. So we basically create a query workflow, and from the query workflow, we can exactly say which time of query can be concurrently computed, which one can be computed in a pipelined way, and which one instead needs coordination. Yeah, this is the conclusion. And I basically develop a new synchronous computational model, a new declarative language, the theoretical foundation that are behind this language and this computational model, and an algorithm to automatically parallelize the queries. And these are the publications. Thank you.